There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our video for the new direction of physics. So this is video 9, the self-interacting field theory. We're going to continue on the microworld. So the last video we talked about the microworld. That's what we talked about, the quantum potential and the potential of self-interacting field theory are the same, but different by a scale of Dirac, large number, 10 to the 39, 10 to the 40s. So we also talk about why all elementary particles split in half, okay? Why the general magnetic ratio is 2. Also, we talk about Pauli exclusion principle, okay? That's all a lot of people in high school already learned that. Now we know why, okay? So we're going to continue on this. So that's the next 3 topics we're going to cover, okay? 3 sections we're going to cover. So the Einstein quantum assumptions, now modern version E equals h bar v, okay? Yeah, so it divided by 2 pi over here, and then times 2 pi over here. So the uncertainty principle, what look like? We will rewrite that, okay? So the 1D trapping of the field, we're going to talk about that. Einstein's quantum assumption, let's derive this. So we have the elementary particle, self-interacting, okay, field theory. The elementary particle will be trapped as a boundary. If we look at it from the top, we will see that the spin will have some field being spun on the equator, okay? We're looking from up and downward. So we see the elementary particle like this. We will have the energy being spinned off near the equator. So if we assume all elementary particles composed of a self-interacting field made by this field and being trapped due to the field self-interacting, like the strong interaction. All elementary particles are like that. They are self-interacting. The field are trapped in the particle, all the field together, okay, like strong interaction. When the in the electron, the more binding because it's smaller. Let's assume the electron's energy, okay, it's on the equator part. So we're looking from top to the down, but you see that we have some energy around the elementary particle on the equator. So this is a force, okay? If you see this format, it's G times m divided by r squared, okay? But now we change it into S, okay? So that's the mass of the parent particle. We take a small section over here, okay? So the small mass, we're rotating around that. That's a gravitational force or self-interacting force. That's a centrifuge force. We write it into the spin, okay? So, it's supposed to be mv squared over r. But if we write it into the angular momentum, we need times r squared. So we will see that, okay? So that's what we see. At the boundary of self-interacting, that's the beauty, okay? At the boundary of self-interacting field, the scalar, if it's a scalar part, we need this equals 1. That's the boundary. That's the condition of the field being trapped. Also, the carry extreme black hole, the general relativity, they also gave that. But the Schwarzschild black hole, that's not rotating, okay? So it's like that, okay? So let's assume, because the elementary particle is rotating very fast, let's assume that. So we have this equals 1. If this part equals 1, then what we have? So we take that, that's mk divided by rk. Because Sm divided by rk equals 1, because we have that. But we need rc squared. In order to do that, that's S equals 1. Okay. Now if we times c squared on both sides, okay. But we have Sm over rk equals 1. Sorry, we have c squared over 1 over here. We times c squared on the top and on the bottom. So that's what we got. Okay. So now what we have, okay, we times the mk from this side to there. And okay, so that's what we got. Okay. So we still have an rk over here cancelled on both sides. Okay, so if we have rk over here, then we became rk cubic over here. So if we divided by 1 rk, we got something like that. So now if we sum all these rk's, okay, all these jk, all these elementary particles around the equator, okay, so that's what we get. In order for the energy to escape from the equator, so all the energy goes in the same time. It's like a ring of the energy. Of this energy, everywhere they equal. You cannot have one part that goes away. You have to have goes like a ring, goes out, okay? So, yeah, when they were smoking, they spin out a ring of smoking, just like that, okay? So, if the energy run away from the equator, okay, from the ring, that's what we got, okay? So then if we rewrite that by 2 pi r, and then that's what we got, okay? E equals h bar v, that means we rewrite, that's what we got, okay? How do we get from here, okay? So the Newton's law of gravity, the force, or the strong interaction or self-interacting, whatever you call it, self-interacting force equals the centrifuge force. But we have a boundary condition, okay? S mk rk c squared equals 1, okay? That's our boundary condition. Once we have the boundary condition, we just play with the mass. We see that it's the angular momentum times the frequency of the rotation. That's what we got. So that means all energy escaped from the elementary particle. If they're equal ring, they're going away from the elementary particle. That's where it's going to happen, okay? So this is why the photon or all the energy has to escape from the elementary particle. They became like that. So this is Einstein's energy assumption. Where did it come from? Because of the boundary condition. With the boundary condition, everything is simple, okay? So the next one. So the uncertainty principle, okay? People talk about that if you have a distance, okay? Now we have a particle over here, okay? Now we have a particle, okay, like this. So if we're trying to measure its momentum and its distance, once you get into very close to the elementary particle, close to the particle, because then the self-interacting field spin off from the equator, okay, will interact, okay. So now if we're getting closer to the object, okay, then the force, because of the strong interaction or self-interacting force, self-interacting Newton's law of gravity in the microworld is so big, okay, so that when we use our macro physics or our current physics, if we're trying to do a measurement, we will see that there is so much energy exchange. So this is why something like that, okay. Now if we divide it by, if we do some arrangement, we will see that because this is something equals 1, okay? So, sorry, the c squared, okay, we need to times c squared over here, okay? Yeah. So, something like that, okay? So this is where if we assume u equals c, that's where the energy momentum change. If we see that, that's like the strong interaction, okay? Or the self-interaction in the microworld. Self-interaction in microworld, okay? Okay, that's what we see. So the quantum interaction, because we have a boundary condition, we can put the boundary condition back. We see that the uncertainty principle is still related to the strong interaction, or the self-interaction force in the microworld is so strong. Or we call, if it's proton, we see that that's strong interaction. So we see the quantum interaction property because we're outside of a trapped strong interaction field. Because the field being trapped, because the 1D trapping, we need to remember that. 1D trapping, okay? 1D trapping, okay? Okay. If we have 1D trapping, then what's happening that the field goes out and come back, goes out and come back. That's the quantum behavior. We can see the quantum interaction of the microworld because we're outside of a black hole. Okay? If we're inside a black hole, we see the 3D trapping in the previous video. We see that it's basically Newton's law of gravity. But once you get outside of the boundary, you will see only the interaction from the equator. And also, it's 1D trapping. They reach out and go back, reach out and go back. Or they have a ring of energy being escaped from the original parent particle. Okay? So the next one, that's the uncertainty principle because of the interactions, of the quantum interactions. Okay? But the quantum interaction property, it's a strong interaction in the microworld. Okay? So let's see 1D trapping, okay? Because when in all graduate school people who studied quantum mechanics, you have a box, okay? Put a particle in there, you see energy of this particle, it's quantized. The energy of the particle inside the box is quantized. What we do is over here, we do something. This is like the interaction constant from the self-interaction or from quantum interaction, okay? So what we see when we have the virtual particle or particle emitting from to the left side and to the right side all equal, okay? But when we're getting closer to one side of the box, because we're not reaching to the other side of the wall. So what we're going to see, one side of the wall, okay, then we're coming back. When we get into the closer to this wall, we're going back, okay? But in order for this to be stable, you have to have a very general energy emission pattern, okay? If the emission pattern is not correct, then when you are getting closer to the wall, you still don't have enough reach out to the wall of force, reach out to the wall. So basically, what I'm trying to explain over here, the quantum interaction, you have the particle emitting a force on both sides. You reach the wall, you go back, and you reach the other wall, you go back. So it has to keep going back and forth. So, but if you are not in the right energy pattern, then you hit the wall, not enough force, then you keep going outside of the wall. So what I did is I did a simulation of this, okay? So the 1D trapped into a box, okay? What I did is just like the previous slide, I showed it over here. So if you put the energy momentum over here, okay, a certain initial momentum, and let the particle move, okay. So, but you see that if we put a certain energy, you see the patterns, okay. But if you don't have the right energy, okay, if you don't have the right energy, the particle goes out, okay. That's the distance between the box, okay. So now your particle being moved back and forth between the particles, okay. We have the distance of 1, distance of 1. So you see the particle moves out, okay. You can play with this, okay, with a model. It's going to keep going if you have a certain energy in of the particles, then you will have the quantum property. If your energy is not right, then they're escaping. So that means the energy is quantized in a box, okay. It's because of the 1D trapping of the field. You have to have a certain energy to be able to balance so that you keep going back and forth in a harmonic way, okay. So, I mean, anybody who can play with this, you will find, I hope somebody with good computer background to be able to do a very micro, because the microworld is so small, we need to have the distance so that we do a lot of smaller grid, okay, so that we have a pattern. So the particle, you will find that as a certain energy, initial energy of the particle it has in the box, you will see it's quantized, okay. So this is where, how to say that, we are already into something where we think it's interesting. So how the 1D field is emitted at what frequency? I mean, you need to change the pattern. We don't know how the microenergy being emitted, okay? So this is why I'm doing this video, to hope to have more people involved in this theory to revisit quantum mechanics from a different direction, okay? So this is, I hope it's the first example where I put very simple 1D trapping, the field goes out, come back, goes out, come back. So keep doing it. So how the 1D field is emitted, at what frequency, that's what we need to understand, okay? So in a summary, let's say that we explained the 5 foundations of quantum mechanics. The Pauli exclusion principle, because of the allow particle to interact from equator, because that's only spin up and spin down, it's allowed, so that at the touch point, they are in the same direction, so that they are not colliding, okay? So that's the very popular Pauli exclusion principle. We can explain it very easily, okay? So the Einstein's energy condition, it's because of the boundary property, okay? Or the self-interacting black hole interactions. That's because of the boundary S m over r c squared equals 1. Because of that, we have a centrifuge and microworld gravitational interaction, okay? So gravitational pattern of interaction, but with a boundary condition, okay? The uncertainty principle is because of the interaction from the equator of the internal motion and the external motion, okay? With a spin as a source of uncertainty, because when you spin, you have energy come out and go, keep on come out and go, come out and go, okay? So what I think, based on this last video and this video, we see that the elemental particles has a self-interacting field as the internal structure. The quantized can be very similar to Planck's idea for black body radiation, but this time now it's for virtual particles, okay? What I'm trying to see that because of the 1D trapping, field goes out and come back, field goes out and come back, okay? So that means we can start to explore the internal structure of all elemental particles. Now what we have in order to understand the quantum mechanics, we need the virtual particle emission patterns and the frequency, how much energy is it's spin off from the elemental particles. People come back and say, hey, Q, we still have infinities. We need to remove the infinities. Okay? So what we need to do, we need to find the self-interacting wave, how it's interacting. Okay? Because in the microworld, the interaction of the self-interaction is so strong that we need to study very carefully on the patterns, how it's the particle being emitted. Okay? So in the next video, we're going to talk about scaling factor as dynamic variables. What's that? Okay? So because we have infinities, if we don't introduce a new scale to remove the infinities, we're not going to be able to know theoretically because we have infinities. Okay? So basically, if we have something, we have a variable, observable, let's say observable equals infinity plus a certain number. Okay? So that's the trouble of the current quantum mechanics. Let's see if we introduce a scale factor for all physics equations. Okay? And then we will be able to re-gauge that factor, okay, and be able to remove the infinity. Okay? That's what we're going to do. In order to, we have quantum mechanics, okay? We know that from this presentation, we see that we have the virtual particle pattern, okay? But we need to get rid of the mathematical infinities. How to do that, okay? So besides the self-interacting, this is the next proposal I would like to propose mathematically to remove the infinities so that we can, now if this infinity is gone, we can study physics. Otherwise, we can't do anything because of these infinities. We need to remove this infinity. And fortunately, I found something which is interesting. By studying general relativity, I found that we need a scaling factor, okay, to bring the self-interacting field theory to a tensor field. So this is why we have to add a scale factor, okay. So that's the next videos, okay. Thank you.